Hello everyone, and welcome to this edition of our Cassandra Community Webinar Series. Today we will be looking at understanding how CQL3 maps to Cassandra's internal data structure. And I am very excited to have with us John Berryman, recently an MVP for Apache Cassandra, and he is a big data architect at Open Source Connections. Also sporting a great No Shave November, but John actually looks like that all the time. So before I introduce John, I'd like to hit a couple of housekeeping items. As always, please use the Q&A tab to answer any questions, to ask any questions during the webinar, and John will answer them at the end. And then also I would like to draw your attention to our new DataStax Academy. We now have Java development courses available for free on DataStax Academy for Apache Cassandra. The link is on your screen now. And we will be pushing more courses live in the coming weeks. I'll also put this link up at the end of the webinar. So without further ado, let me hand over to John Berryman. John, thank you very much for joining us today.
Hey guys, it's really great to be here. I'm rewinding to the beginning of my talk. So yes, today we're going to be talking about CQL3 and the mapping between this new way of querying into Cassandra and the underlying Cassandra data structure. This is so that we can take full advantage of the speed and efficiency inherent in the underlying data structure. My name is John Berryman, and I work with Open Source Connections. To give you a little bit of background, historically we have done a lot of search solutions. We were one of the earlier Solr shops, but as search becomes a bigger and bigger data problem, we've been extending into other interesting realms, and Cassandra is one of them. In my last Cassandra project, I had to work with the customers for the first time to help them kind of understand CQL3 and what that meant for their work there. And what you're seeing today is in large part the understanding that we gained during that time. All right, so a quick outline of what we're going to talk about today. I want to first talk about the problem that CQL solves. And a lot of that is going to require us to dig back a little bit into the underlying internal Cassandra data model. We will then point out some of the issues, like usability issues surrounding the use of the old Cassandra paradigm, and then we'll introduce CQL, which proposes to solve a lot of these issues that we've seen in the past. The most important part of the talk, of course, though, is going to be this lengthy section about understanding how CQL maps to the internal Cassandra data structure. If we have time after that, we will get into some of the neat special sauce about CQL as it regards to sets, lists, and maps. And then I'll conclude with some remarks just to pull it all back together. All right, so let's talk about the problem that CQL solves. As we get into this, obviously you're all here because we know how awesome Cassandra is. So just a quick review. Cassandra is a distributed columnar data store. It has no single point of failure. Everyone knows about the CAP theorem. Cassandra is optimized for availability. Though somewhat unique, Cassandra is also tunable so that if you really want consistency, you can have that with the same technology. Cassandra is optimized for lightning fast writes, while at the same time being quite performant with reads as well. Cassandra is easily maintained and almost infinitely scalable. We've seen clusters get up to hundreds of nodes, and it appears to basically still be linear. So it's a really an amazing technology. But Cassandra does come with some usability challenges. If you're coming from a SQL background, then you have all the same questions about NoSQL certainly levied against Cassandra. People that are used to SQL are going to wonder, where are my joins? How do I put my data together? What do you mean there's no schema? I don't care about flexibility. I want to be able to to talk about the data and denormalize, why on earth should I shove everything about this object into one big flat table? It just doesn't make sense from an old SQL perspective. With Cassandra, more specifically, Cassandra is a big table type technology. And so, with SQL, you're used to a finite and usually fairly small number of columns in your tables. And it's baffling at first to understand what on earth you could do with a table that can take millions and even, in extreme cases, billions of columns. So CQL provides kind of a gap between that somewhat difficult use case in the past and just being able to address the Cassandra data structure with a more familiar syntax that implements the best practices and abstracts away some of the dirtier details so that Cassandra going forward is going to be just really fun to use and really simple. So in order to really dig into this, let's get down to basics and talk about what the Cassandra data structure looks like. At the highest level, you have keyspaces, and these are analogous to databases inside the SQL world. Within the keyspaces, you have column families, which would be analogous to database tables. Within column families, you have many rows, and the rows have many columns themselves. Zooming in on an individual one of those rows, we see that a row is actually composed of a couple different things. Rows have row keys and several different columns. And within a column, there's even more structure. Columns have column names, columns have column values or tombstones if you just want to acknowledge that this column is dead and does not need to be returned in a query. Columns have timestamps to talk about when they were created, and kind of interesting in Cassandra as opposed to some of the other technologies, columns themselves can have time to live, so you can tell data to clean up after itself once the data is stale and you no longer need it. It's important to understand a few more details about the data structure here. All of the elements here, the row keys, column names, and column values, have types. So if you tell Cassandra, hey, this is forever and always going to be a date, Cassandra makes it pretty easy to encode date, string, all the types that you're used to. Column names have comparators. And what this means is that when you stick a column in, it's going to be sorted and it's going to go to the appropriate place in a row according to the sorting that you're using. Different from the column names, row keys have partitioners, but not comparators. The partitioner is going to let us, if we have a row, it's easy to find the machine that row belongs in. But since rows are effectively not sorted, you're not going to be able to find the next row trivially at all. So the use case is often to look up rows. Rows can have any number of columns. One row to the next, you could have 5 columns in one row and 1 million columns in the next. And to that point, rows can have tons of columns, millions. I think the hard limit is 2 billion currently. It is a common use case to omit column values. Time to live is useful, as I just indicated, and tombstones is also very useful. All right, so this is a fun slide. This is where we're talking about why Cassandra is so very fast on writes. On writes, there's almost nothing to do. The first thing you do is you take the new column that's been submitted and you add it to the skip list, the mem table. The mem table internally is implemented as a skip list, definitely worth a Wikipedia read. Really neat data structure that has efficient inserts, deletes, scans, and reads at the slight expense of a larger data footprint, larger memory footprint. At the same time that we're sticking the column inside the mem table, we're also submitting it to a commit log, which effectively is just a spinning platter, and you're always writing to the end of it. Because we're not doing any seeks on the commit log, it's lightning fast, and often what you'll find is that rather than being I/O bound, which is true in a lot of technologies, with Cassandra, you're actually CPU bound before anything else. This is great because the CPU in general is still going to be lightning fast, and also gives you a really good understanding of how to scale Cassandra. Typically, if one core on one server will give you about 3,000 to 4,000 ops per second, and if you know exactly how many ops that you want, it's just an easy math problem to figure out how many cores you need, and the scaling is nearly linear. Reads get a little bit more complicated, but it's important to understand that because when we want to use the Cassandra data model well, we need to understand how data is going in or being read back out. The first thing you do when you want a column or a slice of columns is you check the mem table. And if you find what you want there, that's easy. You return it back and you never have to hit the disk. If you don't find what you want there, then there is a row cache. And if you're lucky enough to find the data there, then you can take it and go back to the user. If you still have to look for more data, then you're going to have to go to disk most likely. The first thing you do is check a Bloom filter, another really cool data structure. And the Bloom filter is going to give you a hint about which SS table on disk you need to go to. The key cache, which is also in memory, is going to tell you which part of the SS table you go to. So that's going to save you another step at least in the lookup. And finally, is the last step. You go to the SS tables, collect all the data you need, and provide it back to the user. This process is naturally not going to be as fast as the writes, but it's still quite fast. And it's important to know that it's going to be faster to find slices of columns, the ordered columns, than it's going to be to do random access. And certainly, I want to iterate that you're not going to do slices of rows, because columns are ordered and rows are just partitioned. So when using this data structure directly, which has been the way that we've done it for years, there are some pain points involved, and I'll try to jump through them pretty quickly. Let's take an example of Twitter, and let's pretend for a second that Twitter backs all their tweets and timelines with Cassandra. If I want to submit a tweet, then maybe I'll do something like this. I'll create a column family named tweets, and then using this pseudocode that looks kind of like the old Cassandra CLI, I'm going to go to the tweets table. I will go down to the John Berryman row, and then I'll go over to a column named a date. And this is how you can get so many columns. You can actually name columns according to things like dates. I'll go to the 9:20 in the morning date, and I'll say, wonderful morning, this coffee is great, and that's what goes in the column value. Later, 9:21, oops, smoke is coming out of the SQL servers, and then 30 minutes later, well, now my coffee's cold. And all these entries are columns that go into the same row, John Berryman, in this data structure we've been talking about. So when you want to retrieve all of John's tweets, it's pretty simple. You just get that row, and you'll get a sorted list of all the tweets sorted by date. The pain point, and we're only starting to see this here, but the pain point is there's no schema. And while it does provide a lot of flexibility, think about what's going on here. We have a table called tweets that is keyed by a string. The column names are dates, and the column values are strings. But there's no real hint in the schema. There is no schema, after all. There's no hint about what those strings and dates are used for. In order to find out what we're actually getting at, you have to read through the code, and obviously that's not going to be very easy to extend and develop with. All right, so let's look at a more complex pain point that kind of gets to some of these solutions that are built in CQL. Timelines are going to be more complicated than tweets. With timelines, not only do we have to record the tweet, the actual text, but we have to record who said it and probably a bunch of other metadata as well. Because it's not just me, it's everyone that I follow. So there's several bad options here, and we'll look at all the uncomfortable options and then talk about the best option, and then we'll move directly into CQL and show how it implements the best option in a carefree way. So bad option number one. Maybe it's okay to create two tables. One that stores the people that sent the tweets, and another that stores the text of the tweets itself. So if I'm following my colleague software, Doug, then I could insert his name in the John Berryman row of the timeline from column family at the appropriate time. And similarly, I submit the same, his text in the John Berryman row at the same time. And then when it's time to actually retrieve everything, I make two requests, one from the from column family and the other one from the text column family. Pain point here is kind of obvious, right? I'm making two requests, and really it wouldn't be two, it'd be several, because there's a lot of metadata that's associated with a tweet. Another bad option is, you know, maybe it's okay to just have one table if we just shove everything into that table. And it looks great at first. So, you know, same scenario. We go to the timeline table, find the John Berryman row, and go to the date and insert something that looks like JSON that we can parse on the client side. From Software Doug, tweet, hey John, I posted on Reddit, upvote me. There is a backstory to that. Check out my blog. I made a post about it. If you wanted to get the timeline back out, then it's pretty easy. Just get the timeline, one query, not too bad, right? Pain point comes when you want to update stuff, because, you know, Cassandra is really fast at writes, but if I wanted to update anything about this, I would first have to read out that element, update the, you know, either the text or the from to fix it, and I have to insert it again. And as you guys probably all know, a read-write use case is kind of an anti-pattern with Cassandra. The last option is the best option, although I'm sure you'll agree it's a little bit confusing at first as well. It makes use of composite columns. So back up a little bit, something I didn't quite mention yet is that columns in Cassandra, the column names are typed, but their types can be composite types. So instead of just having a date or an integer or text, I could have a column name that is date and text concatenated together. And if I use this, I can use it for an interesting pattern like this. I can still have one column family, but instead of inserting you know, one column for the tweet, I insert two columns. The first column, I go down to the John Berryman row, and for a column named by the time and the literal text from, I'll insert Software Doug. And for the same column family, I'll go to the next column over, which is going to be the date and the literal string text, and I'm going to put his tweet there. And when it comes time to actually pull down all the timelines, it's not that bad. It's still just one query, and I've got more columns I'm pulling down, but Cassandra is going to be fast at that. It's basically sending the same amount of information across the net. This resolves a lot of the prior pain points and scales very nicely. So it is a good option to use. The obvious pain point, though, is it's confusing, right? With the composite column name, there's even more code reading to wrap your mind around what's going on. And so what you'll find a lot of times is people building, you know, their own basically ORMs in front of this stuff. One last pain point, in the interest of time, I'll just rush through it. If you have really long rows, such as Justin Bieber's timeline, then you might surprise yourself to find out that 2 billion columns is not quite enough. If you happen to be in a situation like that, then you can also use composite rows to chop up columns into something like, in this case, Bieber months. So same pain point, a little bit hard to read, but it does scale well. All right, so finally, let's introduce CQL. CQL is the Cassandra query language, and it is a reintroduction of the idea of a schema, so that no longer do you have to read through the code to understand the data model. You can communicate it efficiently by something that looks just very similar to a MySQL table construction. Cassandra creates a common language that everyone can use to discuss stuff, because prior to CQL, everyone was directly addressing this Cassandra data structure and building their own layers on top of it that often did very similar things, but not exactly the same thing. So there's a lot of gotchas. CQL is the standard. CQL is a best practices interface to Cassandra. So what CQL is going to do is basically it's going to implement the composite row, composite column name ideas that we discussed in the past 2 slides, but you don't have to worry about the details because we agree the details there were a little bit messy, but you do get the benefit of nice scalability, and you'll see that it's easy to read. All right, without further ado, let's take a look. Here's a quick introduction to the array of things that you can do with CQL. Let's create a table. This is users. We have 4 fields: ID, last name, first name, and date of birth. You can have field types, all the types that you're familiar with, and primary key. You know what that means. It's just the same idea basically as MySQL. Insert. This basically, again, is MySQL syntax, and it's easy to read it and understand what's going on here. Updates. I can find a row in there and insert update stuff as you expect to do. And finally, selects work, at least for simple selects, work just like they would for MySQL, and the results look pretty much like they would. Pretty neat stuff, right? So you might be thinking, sweet, this is exactly the same as MySQL. Yeah, well, you better wait a little bit. There's some interesting intuition. There's good intuition that you can gain from a familiar syntax, but it's important to understand the differences because some of the intuition can be misleading. So some of those of you who have been using Cassandra a while might say, what happened to all the wide rows? Everything's a short MySQL-looking row again. Well, they're still there, and it's important to understand how CQL is rearranging the information you're putting in and presenting it on the screen so that it doesn't look like a long row anymore. And so that's what we'll talk about in the next 15 minutes or so. During this discussion, there's a few important things to remember. Cassandra is good at some things and bad at others. Cassandra can find a row really fast. Cassandra can scan through the sorted columns very fast. But keep in mind that Cassandra does not scan through rows. They're only partitioned. You can't find the next row. So, all right. So in this discussion, we're going to follow a pattern. Several of the slides from here on out are going to look similar to this, where in the top left, we have CQL syntax to create a table. In the top right, we're going to have some data inserted into the table. So you can do this with a CQL insert, and then a select would provide this data back. And in the bottom, we're going to have the representation as it would look inside the Cassandra internal data structure. And I guess it's important to make a note on vocabulary here. When I'm talking about the CQL organization of things, I'll talk about the CQL rows, the CQL fields or columns. And when I'm talking about internal Cassandra data representation, I'll talk about Cassandra rows and Cassandra columns. All right, so let's back up. Quick sip of coffee. All right, so simplest case is we create a table for employees. This table has 3 fields: name, age, and role, and name is the primary key. Stick some quick data in there. That's me, and that's the boss man, Eric Pugh. And the way this would look inside Cassandra is like this on the bottom, 2 rows. Now, it might be a little bit deceiving at first because they look pretty much the same, don't they? There's 2 rows in both cases, and it looks like there's 2 columns. But note that there is a difference. On the internal representation, there is actually only 2 columns because the CQL representation, there's 3 columns, but since we have labeled name field as the primary key, that is telling CQL that, hey, the value of this field is what we're going to use for the row keys, and the field names that are not in the primary key are what we're going to use for the column values. So keeping in mind what Cassandra can do well, we can find an employee very easily because key row names are partitioned. Let's get a little more complicated. In this case, we've effectively got the same table, but we've added a company field, and we've changed the primary key to not just be name, but it's a composite key, a compound key of company and name. Adding a little bit more data in this time, you see that we've got a couple different companies, the same entries for Eric and myself, and then some people from the other company. And the internal representation looks like this. So interesting, right? In the CQL structure, we have 5 rows. In the internal Cassandra structure, we have 2 rows. Is that surprising? The primary key is the thing that you always need to look at here. The primary key gives you the understanding of how Cassandra is going to rearrange its data. Whenever you see a primary key, the first element, and if the primary key is not composite, it would be the only element. But the first element of that primary key tells Cassandra which thing to use as the row key. So in this case, we're going to go to the company, and the values of the company field are the names of the row keys. In this case, we have 2 companies, and that's why it corresponds to 2 rows. Now, it also gets a little bit more interesting this time with the columns, because the primary key, again, is kind of your hint here, but the elements after the first element in the primary key, in this case name, tell you what values are going to go in the column names of the internal representation of Cassandra. So take, for instance, those top 2 rows in the CQL version, Eric and John, right? Since name is the second element of the primary key, then the actual name is going to be encoded in the column names for the internal data structure there at the bottom. Let that absorb for a little bit. We're actually storing the data in the column names itself. And these are composite columns as well, because if we want to know which, Eric has 2 columns in the internal representation, but one of them corresponds to age, so we concatenate that column name with age, and the other one corresponds to role, and similarly for me and everyone else here. So things have become more complicated, and certainly you can start to see why you would not want to directly address the internal representation. But CQL is providing you with a very nice syntax, and is taking care of all the kind of complex work to get all the performance and functionality that you would want out of Cassandra using this strategy. Keep in mind the second thing, Cassandra is good at finding rows by their partitioning, and Cassandra is good at finding slices of the rows based on the sorting of the columns. So, for instance, I can go to your company by row, and I can find all employees whose names start with A through M with a really efficient query. All right, pulling out all the stops, let's create a table with 6 fields, and the primary key is got this kind of weird syntax. It's a composite key. Sorry that this is a little bit hard to read, but do keep in mind that this will be posted, and this should be a good reference for later. But I've named all my fields with letters to capital letters to conserve space, and I've named all of the values as lowercase letters. So once we add data into this, the internal representation is going to look like this on the bottom. Might be a little bit confusing at first, but let's break it apart. I told you in the last slide that the first element of the primary key is what you're going to use for your internal row names. And it's still the same case here. The only difference is that here, the first portion of the primary key is a composite, A and B. So how many pairs do we have in those first 2 columns, A and B? We have 3. So that's going to correspond to 3 internal Cassandra rows. And next, the remainder of the primary key tells what values are going to be stored and used to sort by in the internal column names. And so we're going to pull out values of C and D and use that as references to the column names. And finally, the things that are not mentioned in the primary keys get concatenated to the internal column names so that we can look things up. So take as an example the last row from the CQL version in the top right, STUVWX. What does that correspond to? Well, we need to find the row that is going to live in. And the row name is going to be whatever is in these first 2 fields, so ST. Okay, So you can see on the bottom right. And by the way, I should have mentioned this earlier. Keep this in mind when you review this. Everything's color-coded, so you can find exactly where everything goes to by color coding. So ST is the name of a row, and that's presented internally at the bottom right. Next, we want to, let's say we want to find the value of this last column for the last row of the CQL mapping in the top right. What that's going to correspond to is a column named UV, lowercase u, lowercase v, and then the literal F, the name of the field, capital F, and we see that the value of that is X. Now, in the interest of time, I think we have to go on. I understand that that is a little bit confusing, but please do take some time later to go back and look at this. And I think with the help of the color coding, you can get a good idea of how things are being reorganized. The important thing to understand, again, is what Cassandra is good at and what this corresponds to when you do CQL. So with the primary key, it's going to be super fast to look up any row that is defined by that first portion. And with the primary key, Cassandra is going to be super fast at looking at any slice that is composed of the values in the latter two portions of the primary key. The fortunate thing is that you don't have to do any of this mapping yourself. CQL takes care of it, so that as long as you have a rough understanding of what's going on, your ability to specify the syntax, the schema is a lot simpler, and you're going to get a lot more work done with Cassandra than you otherwise would be able to. All right, so we've got about 10 minutes left. I think we've got a little time to go over kind of a neat thing that you can do with CQL revolving around sets, lists, and maps. These are collections. And this is something that last I checked, MySQL is not going to do for you. I think I've started to see some of these things appear in your more standard databases, but only as kind of a response to the whole NoSQL push. Sets are going to hold lists of unique elements. Lists are going to hold lists, obviously, but they can have repeating elements, and lists are going to keep track of the order. And maps are going to hold key value pairs so that you can give a key and get the value back. The cool thing about how sets, lists, and maps work with Cassandra is it's using the same old data structure that I showed at the very beginning of the slides. So once you understand the mapping, then you can understand very clearly what Cassandra is going to be fast with, why some queries will and will not work. Let's dig into exactly what this looks like. So declaring a table with sets, lists, and map is pretty simple. Basically, you use this templated syntax here at the bottom to define sets with whatever data type you want, lists and maps with whatever data type that you would want. It's important to know that the primary key cannot contain any element from a set, list, or map, and intuitively that should probably make sense, right? All right, sets, lists, and maps have some nice syntax surrounding them. You can insert into a set using curly brackets. You can insert into a list using square brackets. And you can insert into a map using something that looks kind of like JSON. Pretty straightforward, right? Similarly, when updating, you can do a lot of neat stuff with this. When updating a set, you can use this plus equals plus notation. My set equals my set plus new stuff. You can pull stuff out of the set. That's interesting. With lists, very similar. And the semantics here is that you can add to the front of the list, or you can add to the back of the list. That's kind of neat. And with sets, you can add new elements in the set, and there's a couple different ways of doing that as we demonstrated here. And you can delete elements as well. That's just not presented. So we're going to follow the next 3 slides. We're going to look at basically the same organization I used in the previous discussion, but we'll look at sets, lists, and maps and see just how this is working internally in Cassandra. For this table, we create a table that has primary key X and Y, just so you get an understanding of how this would fit in. And importantly, it has a mySet field, which carries integers. All right. So in this set, in this table, we're going to stick a couple different entries, as you can see here. And this corresponds to this internal row. Now think about it from our initial discussion. Does this make sense? It should. The first element of the primary key is the field X. And how many unique entities do we have in field X? We have we have one. So that means it's going to correspond to one row. And similarly, Y is the Y field is the second part of the primary key. So the values of the Y field are going to be stuck, concatenated into the internal column names. See, there's B and C. Now, the cool thing about sets is their value also is concatenated and stuck into the column names. So you can see in the green example that we have two elements, and you can see right where they go, 1 and 2 in the column names. Now, that might be puzzling at first because you're actually not using any values inside the column values themselves. Just keep that in mind. So next we'll take a look at lists. And again, same with the primary key is going to be the same thing, so we won't discuss that anymore. But this list has two elements in it. And the way that this would look internally is kind of similar to the last one, but instead of concatenating the value of the list at the end, we concatenate this crazy freaking number to the end, this UUID. And the actual value from the list goes inside the internal column value there. Now, that might be baffling at first, but what you can see is with this UUID structure and with an understanding that column names are sorted, this is how lists encode their order, and this is how it lets you stick new elements at the end or at the beginning. So it's just a slightly different use case for it. And finally, with maps, this is fairly straightforward. I have two examples here, and this is going to correspond to one internal row with two sections, green and blue. And pretty much the key for the maps gets stored, concatenated to the end of the internal column name. And the value of these maps gets stored in the corresponding column values. So it's easy to find the my map associated with row AC, and it's easy to pull out all data that's associated with that. It's not going to be scattered around. It's all going to be sorted there right together, and easy to find, add, and delete as well. All right, this is a messy slide. I do not expect you to read it. Blur your eyes over a little bit and do understand at least what I want you to see here. When you get a chance, look back at this slide and see what my examples are. The way that I figured out how everything works is I looked at it both in CQL and I looked at it in the old Cassandra CLI, which is much closer to the internal data structure. Effectively, if you follow my example here, I basically implement a table that has all the set structures we just talked about, all the collection structures, and then I look at it both inside CLI and I look at it inside the CQL shell. And you can see for yourself exactly how things shift around. So if you ever have a question, and I haven't covered it with this talk, go back to this slide right here, and this takes 5 minutes tops. Run a quick example for yourself, and you'll understand exactly how all these things are wired together. So putting it all together, and we're getting near the end now. From the beginning of the talk, of the talk, you understood that CQL is basically a reintroduction of the idea of a schema. It allows you to easily talk with others about the data structure without having to read code. CQL creates a common data modeling language. Earlier we had a lot of scatter in the client ecosystem with everyone doing similar but not the same thing. Since CQL is the standard, it's kind of the gatekeeper, and going forward, everyone carries the same semantics. CQL is a best practices interface of the internal Cassandra data structure. There's ways that you can treat Cassandra so that it scales really well, but unfortunately they're a little bit complicated. CQL makes it easier by putting a nice syntax on top of that and abstracting away these messy details. Now, since we're at the end of the talk, with this discussion that we've just concluded, you also understand the mapping from CQL to the internal Cassandra data structure. So now, when you have a question about, what's it really doing on the inside, and if you get confused, please go back to these notes, take a look at them, and please do experiments for yourself to get an understanding so that you can make the best use of CQL and Cassandra yourself. And finally, though I didn't get a chance to address this in the slides, we talked about CQL as a syntax, but there is also a corresponding CQL protocol. It's a binary protocol, and therefore, unlike the prior Thrift protocol, which was accessible by many languages, but not all languages, the CQL protocol is accessible by any language that can talk in terms of bits and bytes. CQL is asynchronous, so that means it's going to be really fast compared to the old Thrift transport layer, which is synchronous. Now, that isn't to say that Thrift can be made asynchronous. It can be, but the implementation in Cassandra is synchronous. And finally, CQL allows for the possibility of having prepared statements, which is just going to make it all that much faster. All right, so that's pretty much it. There is my Twitter handle. Basically, just take out all the non-phonetic characters, and there you are. I would like some feedback. Tell me if you liked it, and if you didn't like it, I'd be interested in understanding how I can improve it. Please do take a look at the OSC blog. I regularly blog about data science, Cassandra, and other things as well. Thank you very much, and it looks like we've got a little bit of time left for questions.
Thank you very much indeed, John. I certainly enjoyed it. Great baseline education there around CQL, and we do have some questions coming in. So just a reminder, if you would like to ask a question, please use the Q&A tab inside of WebEx. Post your question there. I will read them out to John, and we will get through as many as we can. While you're typing those, we have another webinar next week, a migration from MongoDB to Cassandra. That is by John Haddad and Blake Eggleston from Shift, two very prominent members in the community as well. And also, just a reminder, Paige, if you could go to the training slide, we do have free online Cassandra training now available at the DataStax Academy link there. So please log on and teach yourself Cassandra in your spare time. Okay, John, are you buckled in for the questions?
Yep, do the best I can.
Okay, I like questions I can answer. So will this webinar be recorded? Yes, the webinar is recorded. John's slides will be available along with the video recording tomorrow on Planet Cassandra, and we will make sure to email you the link and also tweet it out. Patrick asks, are solid-state disks a good choice for the disks when using Cassandra?
Yeah, absolutely. I mean, in general, always solid-state disks are going to be better than spinning Rust, as I've heard it called, and for a couple of different reasons. With spinning media, in case you're going to do any seeks, which you're often going to do when looking for different pieces of the data, you're going to actually have to literally spin a physical object in different directions to find the different pieces of data and assemble it together. SSDs are neat because you can actually hit different places on the disk at the same time. Now, that being said, it still shouldn't be a terribly scary thing to go with spinning media, especially for like the commit log. Basically, you're always writing to the end of the commit log, and even with spinning Rust, man, it sure is fast. You can get. I need to read up on it again, but I think the number was into the gigabytes per second of data rates, I/O rates, as long as you don't seek, as long as you just keep writing to the end. So, hope that helps.
Yes, and we just posted the talks from Cassandra Europe Summit, and there is a great talk about Cassandra on solid-state disks by, I'm blanking on his name now, but he is from Fusion.io, so you can look out for that one. Okay, so this is from Michael. When looking at the tweet timeline example, what about when you have thousands following a single person? For each tweet, do you have to update all of their timelines at write time? What about when someone starts to follow? How is the timeline initialized?
Yeah, that's actually a really good question. And when I was coming up with the example, I thought about that myself. And that would be tricky, right? Cassandra is going to be super fast at writes. But I have a feeling that Twitter here probably still uses some special sauce that I'm not aware of. I would probably do something whenever you have a new user follow, whenever, for example, I follow a new user, then something offline, probably in the Twitter store magic, is going to know that whenever a tweet comes by, it's going to look me up in a list, a very massively parallel process, because this can be parallel, and then write all this to, again, a very large Cassandra cluster. I suspect that they're probably doing something a little bit smarter than that when you have individuals that are followed by thousands and thousands of individuals, or individuals that follow thousands and thousands of individuals. But probably once it gets to that level of performance, they're building their own stuff as well.
Okay, great. And just from Arthur here, if you could rewind to when you were talking about partitioning, what would be the partitioning key in the case that you gave?
I guess it's hard to ask what he meant, right?
I think so. Arthur, if you're there, please clarify your question.
Yeah, my first webinar. So I'll take a stab at it. I don't know if you're talking about the Twitter example or you're talking about some of my internal CQL examples.
I think it was the Twitter example. It came pretty shortly after that Michael question. So.
Okay. So the internal data structure is going to be, or sorry, the partition key in that case is going to be that first element if you go back to those slides. And just remind you that was the username. So we go to the tweets or the timeline column family, and we go to the John Berryman row. That is going to be the partition key. And just to take a little step further, if we were going to encode this a similar problem into CQL, then what does that mean for CQL? That means that in the private key, the first element is going to be the name, the username of the private key. And then optionally, like in the further Twitter examples, what is our second element of the primary key, CQL primary key going to be? It's going to be the date. So this is going to allow us to quickly query, and you can see how it works either in the old Cassandra data structure or in the new CQL. We're going to find the John Berryman internal row and look through a slice of dates to find out a particular set of tweets. So hopefully I hit both sides of that question.
Yes, thank you. If Arthur clarifies, I'll definitely ask you again. Now I've lost the question that I was on. I was scrolling.
No problem.
Okay, here we go. So this one is from Sankar, And Sankar asks, I can understand how Cassandra is faster in row key fetches, but how is it faster on column access? Is the memory address stored somewhere else? Does it fetch the entire column set and then pass them?
That's a great question. And the answer is that although it is still quite fast, it can't be as fast as just looking up a single entity. So that's, if you were to go back to my slide with how reads work, if you're looking up a single column, then oftentimes you might be lucky enough to just pull that single column out of the mem table and you never hit disk at all. If you do want a slice of the data, then there's no way to prove that I know of. There's no way to prove by looking just at the mem table that you've gotten everything. Some of the things might have already been sent to the SS tables. And when that happens, you go through everything in the pipeline. If you're lucky enough, the SS table, the row fragments have been assembled into the row cache, and then you're good to go. But if you're less lucky, then you have to go to disk. Fortunately, there's a lot of things built in there that make that as efficiently as possible. Your slice might not be in a contiguous segment on the disk. It might have been stuck into SS tables at different times. And slowly, Cassandra is going to come to massage the data to work with the SS tables so that typically we try to make that not the case. We try to find data that should be co-located and co-located. But we do at least go through some data structures in RAM before we have to hit the disk. We go through those lovely Bloom filters, another great Wikipedia read, and they will tell you, they basically tell you if your data is included in a particular SS table. They are very low, they use very, very little memory, and the caveat is that they lie to you sometimes. They will never say that data is not located in an SS table when it is. But sometimes they will lie and say, hey, you should look up the data here, and you go to the table, the SS table, and it's not there. If you make it past the Bloom filter, you can look at the key cache, find the exact spot on the disk to start looking. That's going to help a lot. And you basically do, hopefully, just one quick scan for all the places that the Bloom filter indicated the data might be. Reassemble it, stick it in the row cache, and there you go. So I've kind of gone in detail over what that slide was about. The TLDR for this question is pulling back slices is by its nature going to be slower than pulling back individual columns, but amazingly not terribly much so. It's still quite performant. So I hope that helps.
Might be a good blog post topic there, John.
That is a good point. Yeah, you go do that.
Yogesh asks, why does internal representation use first field of the composite key as a row key? Will the order of the fields in the composite key matter when it comes to performance, depending on the structure of the data?
Absolutely. And it's good to think about that. Step back to the 1990s for a bit, and everyone's using SQL. And the way that you model your data is you think about just the way the data is related. You think in terms of this has a that. This has many that's. That has one of those. You're figuring out how things are connected to other things. With Cassandra, the data modeling is a bit more constrained, but you kind of flip it on its head. You think about the questions that you're going to ask, and then instead of worrying about inserting data into Cassandra, into a database in the normalized sense, with Cassandra, you might write it several different ways, just write the same data. And so, as I've been harping on to this point, Cassandra is great at finding the internal rows, great at finding, pulling back slices of the rows according to the sorted columns. So when you think about how you're going to use Cassandra, you need to keep in mind what needs to be fast. If you want to quickly pull out every employee by name according to a company, then what you're probably going to want to do is the example I had of put the first element of the primary key, which becomes the partitioning key, is the company name. The second element of the primary key, which becomes, there's a word for it, the clustering key? I forget, but becomes basically the sorting key, is going to be the individual's names. Now, on the other hand, if you find that you also have a need to pull back people sorted by salary, then you're going to still have the primary key is going to be composite. The first part of it is going to be the company name, but the second part of it is going to be their salary, so that you can pull people sorted by salary. And a little side note on that as well, skip lists is a really incredible data structure, but it encodes everything sorted so that it can be easily scanned in one direction. If you want to sort everyone according to ascending salary, then take a look at the CQL syntax for that, and you can actually order it so that the skip list is oriented to answer those questions really, really optimally. Don't worry if you don't get that right, as long as you're not always reading the opposite direction that the data structure wants to see. I hope that helps a little bit.
Thanks, John. We have 4 minutes left, loads of questions, so if you could keep your answers as short as possible, we'll get through as many as we can. Steve asks, when using primary key A, B or C, D, is each A, B a distinct row? Can I search on AB? Can I search on A?
Interesting question. Yes, you can search on AB. If you try to search on A, and certainly if you try to search on B, it'll just fail. There's no way that can find it. So that is good to keep in mind when you're thinking about how you have to query Cassandra.
Great. Robert asks, is there any performance difference in updating lists by appending versus by prepending?
That's going to be same, either way. Oh, one side note there, do keep in mind that when you pull elements out of the data list, or out of a list, that you have to worry about a little extra performance hit. Let's see. I'm going to forget it right now, but there is a surprising reads and writes on the list structure specifically. I think it says it in the Apache CQL3 notes. It's a slight gotcha, but good to know about. Just an aside. Next question.
Sid asks, well, first of all, he says, nice presentation. Then he asks, I understand that CQL uses native transport different from Thrift. Why is this more advisable for scaling when reading billions of rows compared to traditional Thrift API?
One thing, Thrift is going to be around for a while, so if you've got Thrift, you don't have to drop it. But CQL protocol does provide some nice things that Thrift is not going to have. And I just barely alluded to it at the end of the talk. CQL is going to be asynchronous, whereas Thrift, at least as it's currently implemented within Cassandra, is synchronous. So that means that Cassandra is going to be twiddling its thumbs while people get it requests. So you're going to be able to improve your throughput with CQL. Additionally, CQL does open the door for interesting things like templated queries. I called it something different in the last slide. Yeah, prepared statements. And that's going to make querying Cassandra a lot faster when you're just asking similar queries over and over again.
Okay, thank you. David asks, can you combine sets, maps, and lists into one column family?
Yes, you can, because internally it just does, Cassandra, the data structure, doesn't know the difference. It's just a column name, column value, just like anything else is. So you might be asking that because with counters, you can't combine them together with non-counter columns. So, but in your case, don't worry about it. Yeah, combine them together all you want.
Vladislav asks, could you please explain how CQL indexes differ from keys? Can they be used for row scans? How is filtering by key part different from filtering by index C column?
This is going to be something where I'm going to have to do my homework. But if my intuition proves true, everything on the CQL side is just kind of a nice covering over stuff that is used internally. So the internal Cassandra indices, it's going to use the same thing on it. And instead of looking like you're getting indices for different rows and different points in the rows, with CQL, it feels like you're doing this on MySQL short rows instead. So in other words, I don't really have a good answer for that one, and I probably need to do a little bit more homework.
Okay, last question. Dun, dun, dun. I'm scrolling. Another chap says, awesome presentation, thanks. Okay. Let us, oh wow, so many. Okay, here's just a quick question. Because this is a good one to leave people with. Everything that you've presented today, Marin asks, is all of that available in Cassandra 1.2, or does some of this require 2.0?
Everything, I believe, is available in 1.2. When I put these, the first version of these slides together, I was definitely working with a client on 1.2. Though you might want to look at 2.0 because some really neat stuff has come online since then that makes CQL all the more interesting and fun to use. If you're interested, please look at the Apache CQL3 documents. They seem to be very well updated, and I was even surprised last night as I was preparing for this talk. Lots of neat stuff on the horizon with Cassandra and CQL.
John, this has been a hot topic, so my recommendation would be let's have you give an updated version of this webinar, maybe as it applies to 2.0 early in 2014.
Sure.
I think that would be really valuable. And then, Paige, if you could just put back John's closing slide. I want to leave everyone with John's Twitter handle there. We have not been able to get to all of the questions, so please feel free to hit John up on Twitter. And John, thank you so much for joining us today. We really, really appreciate it.
And thank you, guys. It was a blast. Let's do it again.
Okay, thank you, everyone. And join us next week for our MongoDB to Cassandra webinar with John Haddad and Blake Eggleston. Okay, thank you. Bye-bye.